Let's talk about section 7.3, which is best fit lines and prediction. Here are our learning objectives. So a best fit line, or also called a regression line, on a scatter diagram is the line that lies closer to the data points than any other possible line according to a standard measure of statistical closeness. These are typically calculated in Excel. So we can make predictions with best fit lines. So what is the weight of an animal that's 15 years old? Um, and then what is the weight of an animal that weighs 20 pounds? So here we have age of animals and weight of an animal. It's not very specific, doesn't really tell us what animal, but this example works for us. So if I go to an animal that's 15 years old and I go up to our best fit line, that tells me that an animal of 15 years would weigh about 15 pounds. What is the age of an animal that weighs 20 pounds? So I go to 20 pounds weight and I go over and over. Here we go. That corresponds with an age of 20 years. Not the most fun example, I know. So we need to be really cautious though if we make a prediction with a best fit line. So first, if the sample points lie very close to the best fit line, the correlation is very, very strong and the prediction is more likely to be accurate. Like strong correlation gives us strong predictions. If the sample amounts lie away from the best fit line by a substantial amount, right, that correlation is weak and the predictions are going to be much less accurate. You would not want to use that data to make a prediction. You also don't want to use best fit lines to make predictions beyond the bounds of data points to which the line must fit, i.e. predicting into the past, well, not into the past, i.e. predicting into the future is an example of that. Another thing we need to be cautious of is a best fit line based on past data is not necessarily valid now and might not result in valid predictions of the future. And we don't make predictions about a population that is different from the population from which the sample data are drawn. Like if I did a study on the average amount of years donkeys lived, I wouldn't want to be like, okay, that's going to predict the average life expectancy for horses, right? Like stick to the population that you studied. And remember that the best fit line is meaningless, completely meaningless, when there's no significant correlation or when our relationship is nonlinear. For example, it doesn't follow a line. So let's state whether the prediction or implied prediction should be trusted in each of the following cases and explain why or why not. You found a best fit line for a correlation between the number of hours per day that people exercise and the number of calories they consume each day. You've used this correlation to predict that a person who exercises 18 hours a day would need to consume 15,000 calories per day. Okay, first off, the problem with this is no one can exercise for 18 hours a day, right? You have, how many hours are you sleeping? 6, right? So this should not be trusted. It's a prediction beyond the bounds of data of the data we've collected. Next, there is a well-known but weak correlation between SAT scores and college grades. You use this correlation to predict the college grades of your best friend from her SAT scores. Well, no, the keyword here is weak correlation, right? You do not want to trust the prediction because there's a weak correlation. If the correlation is weak, it doesn't mean anything. Can't use it to make a prediction. Next, historical data have shown a strong negative correlation between national birth rates and affluence. That is, countries with greater affluence tend to have lower birth rates. This data predicts a future high birth rate in Russia. Okay, the problem with this was past data, right? You can't use past data to make a you can't use past data to make a current prediction. Best fit lines in R squared. So the square of our correlation coefficient R squared is the proportion of the variation in a variable that is accounted for by the best fit line. Okay, the square of our correlation coefficient R squared is the proportion of the variation, variation, we talked about variation earlier, in a variable that's accounted for by the best fit line. So for example, if I have R equals 0.5, R squared would be 0.25, which means that 25% of the variation in my data is accounted for by the best fit line. The proportion of variation would be R squared, which is 0.25. That means that 75% of my variation must be due to other factors, and only 25% is accounted for by that line. Political scientists, let's take a look at example 2. Political scientists are interested in knowing what factors affect voter turnout in elections. One such factor is the unemployment rate. Data collected in presidential election years since 1964 show a very weak negative correlation between voter turnout and the unemployment rate, with a correlation coefficient of about -0.1. Based on this correlation, should we use unemployment rate to predict voter turnout in the next presidential election? Well, no, right? We said it has weak correlation. We don't want to use it to make a prediction. So what are some other possible factors that could influence voter turnout? So one, it could be the candidates, right? 2 could be the weather. Can you think of any others? I'm sure there's a ton. The candidates, weather, it could be like location of polling stations, like did they move from last time? I know there was a lot of that going on this past election, which I'm very happy is over. Next, I'm going to mention multiple regression. We aren't really going to focus on this at all, but a multiple regression allows us to calculate the best fit equation line that represents the best fit between one variable and a combination of other variables, such as price by weight by color, right? Certain colors of products cost more than others, which is silly, but I get it. The coefficient of determination, R squared, that'd be like the big R of this squared, tells us what proportion of the scatter in the data would be accounted for by the best fit line. So I wanted to mention this. Maybe if you suggest or you want to take another statistics course, let me know and we could talk about multiple regression. So last, let's use this best fit line to make a prediction. So assume the best fit line for a data set of the heights of males in inches and weight of males in pounds is given by the following equation. Y equals 2x plus 10. So let's predict first the weight of a male who is 64 inches tall, and B, the height of a male who weighs 120 pounds. Well, my height is X and my weight is Y. So for A, we'll do that up here. If I have Y equals 2 times 64, which is my height, plus 10, that means Y equals 2 times 64, that's 128, plus 10, so 138. So the weight of a male who is 5'4", so 64 inches tall, would be 138 pounds. And what if I wanted to find the height of a male who weighs 120 pounds? Well, that'd be 120 equals 2x plus 10. Subtract 10 from both sides. 120 equals 2x. So x equals, that's 110. So x equals 55 inches. Yes, I know that's a little short. but I wanted to make sure we had practice substituting in given values to make predictions.